Okay, so we are back with our NumPy implementation. So if you didn't manage to produce the video before, you can still ask me and I can try to help you. But I suggest we move on to the NumPy implementation of the Laplacian. So you had a few minutes to do this before lunch. I'm going to help some of you if you want, and also if you have some questions on the Discord, and ask them on the Discord, and then we can check the correction in 5 minutes. But it's okay. It's a lot of indexes and stuff like that, so it's a bit tricky to do. You just have to remember to do 2 for loops on the rows of the stencil and the columns of the stencil, and then your whole Laplacian you can compute on it as a whole. Okay. Just something I forgot to tell you before lunch is that I imported all the stencil, all the parameters from a module that I called Grayscode utils that I put in scripts here. So here you have all the helper functions we defined before that we are going to use in every implementation from now on. So I just import them here so that you have access to them in this notebook also. So just remember to execute this cell. And then I suggest we take a look at the Laplacian in NumPy because it's a bit of a mess with the indexes, but the main takeaway is that here we remove the 2 for loops on the Laplacian and we actually use a NumPy syntax. Okay, so we take all the rows and columns of the Laplacian except the borders. So we remove them with this syntax here. One is we take only the first row and the one before last. Same for the column. And we apply the stencil on it. For the stencil, I still did 2 for loops. Maybe there is a more optimized way to do it, but so yeah. So I apply the stencil on it. I apply the stencil on U, and then I get the Laplacian of U. Okay. So try to copy paste the code in the solution in your tutorial notebook if you didn't do it yet, if you didn't manage to write it. And then we're going to use this function, and we're going to compare it to the function named Laplacian loops that we did just before lunch. Okay, so it's the function with the 2 for loops that was very, very slow. So to compare them, oops. You can use NumPy.allClose that Jean-Marc presented before. And this will tell you if every element of the arrays is equal to every element of the other array. So just call NumPy.allClose with the results of Laplacian loops and Laplacian NumPy. And then you can check if you have the same result. And you can use timeit also to time the execution of both functions, so that you notice the speed up once we write the proper the NumPy code. Okay, so try to use them, and then we will compare the results. Okay, so let's compare the 2 Laplacians that we wrote. So for this, I have to initialize my arrays each time I call the Laplacian. Don't forget to initialize your arrays every time you redo the computation. So let's try that. So I call Laplacian loops, I call Laplacian NumPy, and I check if both results are equal. So they are equal, and now what I can do is maybe time the execution of one. And I'll time the execution of the other one afterwards. Okay, so just Laplacian loops was 8 seconds with the very naive Python code. And now that we use NumPy to broadcast all our computation over the U array, let's check. We should have a much more reasonable time. Okay, so this now is more reasonable, 40 milliseconds. So now we're going to use this Laplacian NumPy when we move forward. And so let's try to use it in the grayscale dsteps function, okay? So, whoops. Instead of Laplacian loops here, we're going to call Laplacian NumPy. And then this grayscale dsteps function that is modified, we're going to call it in the simulate images chunk, and then in the other function. So you just have to be careful here to call the right function, but I think it's already written in the solutions. And you just execute each cell. And then you can plot a real video with 10 images, which will be a bit nicer than the one we had with only native Python. Okay, so let's try to do it. If you have some problems until then, feel free to tell me, because once we have seen this NumPy part, we're going to move on with other techniques. So it's good that if you manage to plot the images and the video with NumPy. Okay, so here's going to take maybe a few time, because before with 2 images we had like 1 minute of execution. It should be faster now. Okay, so I produced normally one HDF5 file, which is here. Now I'm going to make my video from it. Okay, I did it. And now I'm going to open my video. So for the people that are on Must, I think I forgot to put a way to see the video, I'm sorry. But for the other ones, you can just see it from your file explorer or for your, okay. So this, oops, it goes fast, is our video with 10 images, okay, and 32 steps between each image. So this is the video we have with NumPy. It's still a bit slow, so maybe we won't do the full benchmark with 1,000 images. But then with Numba and JAX, we're going to try to plot a whole video of 1,000 images ourselves. Okay, so I give you a few minutes to check that. And then we're going to move on from this implementation and try a SciPy implementation. Because maybe some of you noticed, but what we're doing is a convolution by hand, and it's not very easy to do. So maybe it should be better just to use the dedicated convolve function. So we're going to try that afterwards. Okay, so most of you in the room have working code and videos. So I suggest we move on to the SciPy implementation. So SciPy, it's scientific Python, and so it's a NumPy extension, and it's mostly for scientific computations like differential equations, optimization, signal processing. And so you have to import a specific submodule when you want to use a SciPy function, because there are several submodules. And for our case, we want to do convolution. So this is a basic signal processing operation. So for this, we have to use the dedicated SciPy function that is in SciPy.signal. Okay, so we import the module SciPy and the submodule signal here. So let's run this. Okay. And so try to write it yourself, this function, this Laplacian using SciPy. So it should be very straightforward, because it's really a classical function, this convolution. So use the SciPy function from SciPy.signal to do a convolution. You can check the doc online. It should be maybe 1 line here. And then we see the correction together. Okay, so let's check the solution. I see many of you used convolve, but I suggest we use convolve 2D, because I think convolve is for n dimensions, And since we have only a 2 dimensions problem, it's better to use the dedicated function. It's less generic, so it might be more optimized for our problem. And so you just have to call it with your arrays U0 and V0 that you have to initialize. So maybe some of you had problems with sizes, so maybe it's before you didn't initialize your arrays before running the compilation. And here I use the mode equals same and boundary equal wrap to have the same results as the Laplacian that we did with NumPy. So here is the solution convolve 2D. It's very straightforward, it's just one line. But we're going to see why we didn't use it in on the first hand. Oops, I have to run my cell. So let's compare both solutions. So I call time it to time the Laplacian NumPy, and then I initialize the arrays again. And I compute the Laplacian on U0, so a newly initialized U0. Be careful to always initialize them. And I check the difference in computing time. So as you can see, the Laplacian that we defined with NumPy is a bit faster than the one with SciPy. So afterwards, we're going to use mostly the NumPy one, also because SciPy is not always supported with the optimization libraries that we propose. Okay, so that was it for the NumPy part. And then we're going to use this implementation with Numba and try to speed it up. So I'm going to leave you a few minutes to test both solutions with NumPy and SciPy, and then we can tackle Numba in maybe 5 minutes. So I think some of you had an error because you put full here, and so you had arrays that were not of the right size. Here, when you put same, it will produce a result that is of the same size as the argument that you put. So Laplacian will be of the same size as U. So this is what we want here in our problem, but it's just because we did it this way. So maybe.
Can you speak a little louder?
Sorry?
Can you speak a little louder?
Sorry, yes. Okay, so if you had an error on the output size of your matrix, maybe it was because you put mode equals full here and not mode equals same. I think some of you had it. Okay, so let's move on to the Numba part. This is the part we're going to do the real benchmark with 1,000 images because it will be the fastest one. The JAX part, I don't think we'll have the time to do it in to do the full benchmark, because actually it requires quite a bit of modification. But this was what we predicted, so we only stopped the JAX part at some point that is a bit tricky, and then we tell you to come back on the GPU week to fix it. So Numba is going to be the part where we really plot the images and the benchmark and do the benchmark. Okay, so first let's import everything. So I'm in the fifth Jupyter notebook, okay? So what is Numba? It's a just-in-time compiler that will translate Python and NumPy functions into optimized machine code. And for this, it will use the LLVM library. Typically what you can do with Numba is optimize for different architectures like sequential, multi-threaded, CPU, and GPU. So we're going to see Numba only for the CPU class, but we're going to use it in sequential and multi-threaded mode. It works best on codes which do a lot of computations. So codes that have NumPy and use a lot of for loops. So you're going to see a lot of JIT decorators like that. So it's a decorator that we put on top of a function to compile it. And there are some frequently used options that are no Python equal true, that is enabled by default. Parallel equal true when we want to do parallel computation. and fast math equal true that we're going to see also after, I think. So how does it work? So when you define a function with Numba, you can put this JIT decorator on top of it to tell Numba to JIT compile it. And so when you call your function here, you're going to have one part that is translated in the Python bytecode, and the arguments are going to be used, and Numba will inference their type. And so it's going to be, there's going to be an optimized version of it that will be rewritten with the LLVM library. And so all of this will produce machine code. And Numba will store it in its cache. And so whenever you run your function for the first time, it will do this compilation step that is going to last a few seconds. But then when you recall this function another time afterwards, it will use the optimized version that is in the cache, and so it will be much faster. So when you compile a code with Numba, you have to remember to only time the following uses and not the first call of the function, because the first call of the function is going to have an overhead of compilation. Okay. So let's try and optimize our first attempt at computing the Laplacian. So we're going to use the Laplacian loops function because Numba is specifically efficient with for loops that we didn't manage to optimize with NumPy. So you take your Laplacian loops function and you optimize it with Numba. It should be quite straightforward. I know some other people tried the Laplacian NumPy with Numba to JIT compile the Laplacian NumPy, and it was actually slower, which is a bit normal because Numba is mostly suited for loops like this. So to optimize it, so first you have to import Numba, and then, okay, you will have to put a decorator and maybe some other things, I don't remember. So let's try to do this. I will give you a few minutes maybe, but I think it's, yeah, for the moment it should be quite straightforward. Okay, so let's check the solution. So to optimize this Laplacian with Numba, well, I show you one solution that worked, but maybe there are some others. In this whole Numba notebook, I tried to use the solutions that worked best, that were the faster, but there can be plenty. You can JIT one function and not the other. It depends. So here I just put numba.jit. I use fast math equal true and cache equal true, but I still check the results, I think. Well, maybe not here, I didn't. And there is nothing more to add. So let's just run that. I chose to not time the first execution because then I would have an overhead because of the compilation time. So I just run it once. Whoops. And then I time the second execution here with time it. I make sure to initialize my arrays before. But normally time it, you do a few iterations, so you could just call it and then it will tell you the first iteration was very slow compared to the others, but then you would have a kind of a representative median of the time spent, so you could skip the first call here. Okay, so I have my Laplacian with Numba, so now I have to call it in my grayscale function. Okay, so let's check. It's called here instead of Laplacian loops or Laplacian NumPy. I call Laplacian Numba, and then I'm going to have to optimize this function with Numba. So it's kind of the same. Let's do it together. I think that's not very hard. So I JIT it also with the same options. Okay, let's run it. And And I also JIT the reset borders function because this is also kind of a implicit for loop. So let's do it. Okay. And in the last function, you can also optimize it with Numba because you still have a for loop here. So let's do it. Let's do everything JITted. And the IO function, let's not touch it with Numba, I guess. I think I tried and it was much slower. So now that you have everything JITted, you can compare it to the reference. And you can, well, you can time it. And I think the rest of the exercise, yeah. And then you can use it to make your video. So I think maybe this will be the time to make the 1000 times 32 benchmark if you want to run it, but it's not mandatory. If you want to keep to 100 images, well, I think it will be easier. So yeah, let's run that and let's check the results and check if everything worked and if it's not too slow. Some people had trouble opening HDF5 files because it's not straightforward. So here I put a little function just to, if you want to verify, to check that you have the right number of images and the right size in your HDF5 dataset. So here, if I run it after, well, it was on a different test, but if I run it another time, it will give me the right size of my dataset. Voilà. Okay. So I'm running the benchmark, try to do it. Don't forget to put Numba .jit in front of all functions, except the last one that produces the HDF5 dataset because well, it's better to use Numba only with functions that use NumPy and for loops, and that's all. Okay, so let's continue. I hope you all managed to run a small benchmark. So here it's only 100 images, but with the GPUs, we're going to make more. If you want to run 1,000 images, you can, but it will just take you 20 minutes, so do as you want. Okay, I'm just going to check my HDF5 is of the right size. So yeah, it's what? Ah, no, but it's not the right size because I messed up. Okay, so let's move on to the Intel SVML part. So it's just a little trick if you want to see if your Numba uses the short vector math library from Intel or not. So for this, you're just going to print some information about your Numba installation. So you run this cell here. Well, I'm going to stop my benchmark, sorry. And if you have trues everywhere, it means that it's using it. If you have one true and the rest is false, then you're not really using it. So if you want to use it, you can install the Intel package here. So to install it, you can open a cell and just type pip install and the name of the package and just run it. But me, I have it already installed, so I'm not going to do it again. And then, where is the exercise? Ah, voilà. Okay, so let's try to see if we're going to speed up our code using this Intel SVML library. So I've been told it doesn't work on Mac, so sorry for Mac users. So SVML, it provides compiler intrinsics. So it's functions whose implementation is handled specially by the compiler for math operations. So it's better to use it for for codes that have like a cosinus, sinus, roots, log, etc. So on the grace code, we only have additions and multiplications, so we're not going to be able to notice if we use SVML or not in this. So let's try to use SVML on the code snippet here. So it's just a little code that uses cosinus and sinuses, but to compute the identity, I think. Yeah. Okay, so let's run it. You should have an array of ones at the end because you compute one and you put it in your array. So if you want to check whether your code uses SVML, you can do the little exercise here, and then we'll check the solutions together. So to do it, you should check your assembly code with inspect ASM. So just look the documentation online if you want. You put this assembly code in a text file, and then you grep SVML in the text file to see if you have some SVML instructions in your assembly or not. Okay, so I'll leave you 5 minutes to do that, and then we'll move on to the multi-threading. So let's check my Numba install. Whoops. Okay. So the solution I found is just to open a text file and to write inside the assembly code of my function ident loops. Okay, so if you read the doc, this is how you should write it. So I put it in this text file, and then in this text file, I just look for the SVML word. So I use grep. And I use this exclamation point to say that I'm running a terminal function as if I were in the terminal. And so what I can see here is I have indeed SVML in my text file to compute the cosinus and the sinus. So yeah, this was just a way for you to check if you were using this Intel library or not. It depends on your NumPy installation. Sometimes it can speed up the code and sometimes not. So it's on the Numba doc. We thought it was fun to witness, but yeah, you should, if you have a code with lots of cosinus, sinus, exponential logs, it might help you. Okay, so let's move on with the multi-threading. So the first step is to parallelize the Laplacian with Numba's syntax for parallelization. And for this, you can replace the range in your for loops with p-range. So this is how you tell Numba that this loop can be parallelized. So you should not do that on every loop, only loops that can be parallelized. And here in our case, in the Laplacian, we can do it. And if you use this function here, you can click on the link to have the doc. If you use this syntax here, you also have to specify parallel equals true when you decorate your function with JIT. So I'll let you do this, parallelize, and then time your execution to see whether it's faster or not. And check also your results because, well, here it's safe. But if you use it everywhere on loops where you have race conditions or stuff like that, it can mess up your results. So always check that your results are actually good when you multithread. Okay, I'll let you do that, and then you can also use it to parallelize the grayscale dsteps function. Okay, let's check the solution. So here to multithread this Laplacian, I use p-range on both loops of the image, p-range, and then I JIT the function, and I don't forget to pass the parallel equals true argument. Okay. So let's time our execution to check whether it's faster or not. Well, around this, let me show you the call in Grace code D steps parallel. So if we want to parallelize Grace code D steps, we have to be careful because there is a race condition over U and V because it's updated every step of time. So if we want to compute this in parallel, but we cannot the way we implemented it, we can't. So we just have to JIT this function, but we cannot put prange here. Okay, if we put prange, it will mess up the computation because then one thread will update U and then the other one will update it as well. And so it won't work. Okay, so here we notice that our Laplacian Numba parallel on Jean-Marc's computer actually is 3 times faster. You have 4 cores on your computer. Okay. So after we will check the consumption of cores. So okay, let's run this. Let's check the timing of this Grace code D steps parallel function. Sorry, I'm going a bit fast, but we don't have much time left. So. And then we're going to call these functions in our main ones. So okay, so the Grace code D steps parallel is a bit less than 3 times faster. So in the simulate images chunk parallel, I did not JIT anything, and I did not put any prange. It was the solution I found that worked the best. So I guess parallelizing the Laplacian was already enough. And the simulate and save chunk is always the same. We don't touch it. Okay, and so now we can run a benchmark with 30 times 100 iterations. Okay. Yep. So while this benchmark runs, I'll answer the questions if you have some. And for the people that have already done this, you can try to do this, this exercise, compare the number of CPUs used with previous and parallel Numba versions of our code using the method of your choice. So you can run HTOP, but if you run a HPC cluster or I don't know what, you can also use another method. So try to do this exercise, and I'm going to answer questions on the NumPy implementation. And then maybe we'll try to see JAX a little bit, but unfortunately we are a bit late. So do you have any questions on the NumPy implementation? For example, I don't know, satellite sites, do you have questions? If you have also on the Discord, you can ask them. Are there questions in the room on the Numba implementation? No? If you have some questions on YouTube, you can ask them also. Okay, but let's check the solution of how we check the number of CPUs. So we decided to use the function psutil.cpu% of the package psutil in Python. And so when we run it, it tells us the percentage of use of our CPUs. So on Jean-Marc's computer, if you use 100% of our 4 cores, we should have 400%. So once my benchmark is done, okay, so my benchmark is done. I can try it. Now we'll see. Well, and then for the last part of the tutorial, we're going to see a bit of JAX, but there will be a lot of changes to make to the code. So we're just going to change the Laplacian, I guess. Okay. So here on Jean-Marc's 4 cores computer, we use 3.47. So it's okay. All right. So let's move on to the JAX part. So JAX is a Google library that is oriented to machine learning and NumPy type computation. So it's mostly geared towards deep learning, and it's designed to port your code on several accelerators without having to modify it. So you don't have to specify the device you compute on. You can have the same code that runs on a CPU, on a GPU, on several CPUs, on several GPUs, I think. Okay, so I'm gonna go a bit fast, but here is the list of the supported platforms. I'm on the 6 Jupyter notebook, by the way. So how does JAX work? It uses the OpenXLA library. So it's the Accelerated Linear Algebra Library, which is an open source machine learning compiler for GPUs, CPUs, and machine learning accelerators. And it's the equivalent of BLAS and LAPACK for NumPy and SciPy. And so JAX produces internal intermediate representations of pure Python functions. It uses a process of tracing that you might see a lot in JAX errors because we convert most things into tracers. And it JIT compiles the code also to produce a high-level optimized program. And using the XLA library, you can compute on CPU, GPU, or TPU. Okay, so you have a bunch of modules in JAX. So the one we're going to use the most is jax.numpy. But you have also jax.scipy, random, image, LAX. LAX is a low-level interface with XLA that we're going to use also. And you have also debugs and profiler functions that you can use. So why do we have to modify a lot of our code when we use JAX? It's because it uses JAX arrays. When you want to port NumPy code to JAX, you have to port your NumPy arrays to JAX if you want to optimize the computation on these arrays. Here is an example of the things you can and you cannot do with JAX arrays. So the first thing you can do is import JAX. Sorry. Okay. The first thing you can do is install JAX. Oops. So here I installed just the CPU version of JAX, but then on the GPU class, we're going to install the GPU version of JAX. On the containers, for the CPU container, we just install JAX CPU as well. Okay, let's check. All right. So here I define my array as a JNP array. So JNP is the import of jax.numpy as a JNP. And then when I want to sum the array, I have an error. So JAX arrays are not easily manipulable. Yeah, it's hard to handle JAX arrays, so you have specific rules. So let's check them. So first of all, when you want to convert your NumPy array to a JAX array, here you have AFG, which is a NumPy array. If you want to make it a JAX array, you just put jnp.array in front of it. And so you see here, yes, you have a JAX array here, print. I print this array, and this type is jaxlib.accelerate-extension.array implementation. Okay. So one thing that is very tricky with JAX arrays is that they are immutable. So you cannot use the same NumPy syntax that we use to access some elements and to change some elements of an array. So let's check this example here. So we define AJ, which is a JAX array. And then we try to access the first element of AJ and to put it to 0. And it tells us that we cannot do that because JAX arrays does not support item assignment. So, well, fortunately, it tells us the solution. So what we have to do is access the element at index 0 and set it to 0. Okay, so this is the syntax to change any element of your JAX array. You have to do that every time you want to change a specific element of your array. If you want to change the whole array, you don't have to do that. Here, when we print AJ after doing this, we still have the first element to 1 because since the JAX array are immutable, the result here, you have to reassign it to AJ. So I have to do AJ equals AJ.add.set. So it's a bit annoying, but it's how you manipulate JAX arrays, okay? Okay. Yes, question in the room?
So for that last step, when you're doing AJ equals AJ.add, are you like reallocating an entirely new set of memory and then overwriting it?
I'm not sure, Jean-Marc, do you know?
Like, is it,
reallocate
so it's not happening in place, the memory, it's not doing an in-place change of the memory, but reallocating a new array?
Ah, il faut un micro.
What says the JAX doc is here. So when you use the JIT function of JAX, this expression become in place expression.
Ah oui, okay.
You have the reference of the documentation if you want.
Thank you. Okay, so using this add syntax, you can do a lot of arithmetic functions, add, min, etc. So you can see them on the documentation. We have a few exercises. These two exercises, if you want to do them, the correction is at the end of the notebook. Okay, so if you scroll to the end, you're going to have the solutions of the exercises. So if you want to do it, do it if you already know JAX. So, yeah, I suggest we do a quick break maybe, and okay, try to do this exercise, and we will decide what we do. I'm just gonna steal 10 minutes of Sebastian's time to present the last part of the notebook. So, unfortunately, we won't have time to do the whole JAX implementation. The beginning of the implementation is on the 7 notebooks. So, if you're thank you. If you're not here on the GPU session next week and you still want to have an implementation with JAX that works, you can try this notebook, the 7 notebook, and then tell us if you encounter any problem on the Discord or anything. But for now, for these 10 minutes that I have here, we're just going to focus on the 6 notebook. We won't start the JAX implementation of the Gray-Scott equation, And we will do it next week, and we will optimize it. We'll have plenty of time to do it because we have 1 hour and 30 minutes next week just on JAX. So it's going to be implementation and optimization for GPU, everything. Okay, so I'm not going to correct the 2 exercises. I'm just going to skip some parts that we won't talk about today. Let's take a look at the 1.4. It's the constraints to JIT a function, because in JAX you can also JIT functions. So just in time compile them. So you can either decorate your function or do it, call it like a function, jax.jet. So the same as Numba, the first time you call it, the result is going to be cached, so you're going to have a higher runtime. There might be some failures when you compile, because some stuff are not compilable with JAX. And it's very important to understand how you can JIT compile your function, because it can be tricky. So in JAX, to JIT compile your function, you have to have a pure function. So no access to global variable, no access to static function variable. And you have to have output arrays that have a fixed shape. There are a lot of constraints on input parameters that you might encounter as a form of a tracer error. So let's take a look at one of them. Okay, so we have this function here that takes vector x, and axis must be the axis over which we are going to split it in 2. So we split this x vector in 2, and we try to JIT it, and let's see what it gives us. So this is the typical error with JAX, tracer integer conversion error. So it means that there is an argument that we use that is not in the right format for JAX. So for us, in our case, x is a NumPy array, so it's okay. But axis here, it's an integer. And we're going to declare it as static. This is the way to fix this error. So to declare it as a static parameter, which it is, we have to use the partial function from functools. So this is very important. We're going to use it a lot in the Python implementation of the grayscale reaction. So you have to import this module here, and you have to JIT compile your function, but stating that the second argument, so here static argnums equals 1 because Python starts at 0, so the second argument is static, okay? And this is the syntax to JIT compile a function with one argument that is static. And so we say, okay, so the axis is static, so now you try to JIT compile it, and it should work. Okay, so we split our 4 elements array into 2 arrays, okay, following the axis 0. All right, so here is the link to this kind of tricky part on tracing a static variable, so you can check it if you are interested in it. A few notes on how to debug and profile in JAX. So you have several ways. You can use JAX debug.print. Breakpoint also, if you want to put some breakpoints in your code. And to profile, you can use a dedicated JAX profiler. You can open it with Perfecto here, which has a very nice UI. So to check your profiling, it's what we recommend. We're not going to do it in live here. Okay, So the last part is on vectorization, but it's a vectorization as a PyTorch and machine learning, deep learning uses it. So it's not very vectorization as a vectorization in compiler. It's vectorization as making a function, applying a function over a vector. So let's not talk about that. We're going to see it with the PyTorch class. Here, this is also quite important in JAX. The for loop will compile very badly when you JIT them. It's not the same as Numba. So you have to replace for loops with JAX by special JAX constructs. The same as when you use NumPy, you use NumPy instead of for loops. Here you will have to use JAX instead of for loops for a lot of the times. And so these are some kind of function that we will use in the Grayscott implementation. So to replace for loop on JAX, you can use jax.lax.forEloop. We're also going to see how to scan the same computation over different arrays, for example, with lax.scan. So this is all some. These are all some JAX constructs that can help you get rid of the native Python in your code. Okay, I think that's all. If you have some questions, please ask them on the Discord or in the Zoom or in the room. Here there are the most interesting things on the documentation. JAX, the sharp bits shows you that it's not straightforward to use JAX, but the documentation is quite clear. So feel free to check it. And on the next week, we're going to see how to apply it to our Grayscott code. And we're going to run it on GPU directly, because with JAX, you can run it on CPU and on GPU without having to change anything. Okay, thank you very much. Do you have a question? No questions? Okay. So I will give the floor to Sebastian, I think. Yes.